Okay, so this is the second video dealing with electrochemical cells, and in this one we're going to talk about cell potential and overall equations for spontaneous reactions. So these are reactions that occur in galvanic cells and produce a current. So the force that pushes those electrons through the circuit, we talked about the conducting wire, there's a force pushing those electrons through, that's called an electromotive force, or EMF. Used interchangeably are the terms cell voltage or cell potential. And so if you set up an electrochemical cell correctly, as shown here in this picture, you will spontaneously generate an electrical cell voltage. And so that is because of the redox reaction taking place. So let's have a look and see how this works. So a bit of text here, so pause when you feel like it. So first of all, we look at half cells, and we look at what are known as standard reduction potentials. So you've seen that from the tables. So you have a table somewhere in your textbook. It's in the appendix, I believe. But these standard potentials are standard conditions, so standard concentration, 1 mole per liter. If it's a gas, 101.3 kilopascals, that's 1 atmosphere, and 25 degrees Celsius, 298 K. And so those are the standard conditions. And so these conditions mean that when you're looking at these cell potentials, you're dealing with standard states. Now, when we go to look at the table in a second, you'll see different values. So first of all, the zero value. So the zero value is an important value because it's a hydrogen half cell and it's a reference electrode. So a reference electrode means we use that as a reference against other half cells. And so the hydrogen's half cell was assigned a value of 0, and then everything else, when hooked up to the hydrogen half cell, would give a cell potential. And that value depends on what happens. So the negative values you see on the table are when the species gains electrons less easily than the hydrogen. That is, it's going to be oxidized relative to hydrogen, so hydrogen gets reduced. So that species is oxidized. Negative value, species is oxidized relative to hydrogen, whereas a positive value means that species gains electrons more easily than hydrogen, so the species is reduced, and it means hydrogen would be oxidized. So let's just look at that in terms of a table. So here's our table of standard reduction potentials, and so here is our reference electrode, our hydrogen standard electrode. And so, as I just mentioned, anything above it with this positive value would be reduced relative to hydrogen. And so that means these would be reduced, hydrogen would be oxidized, and that would give you a cell, a full cell, 2 half reactions. Anything below it would be oxidized relative to hydrogen, which means hydrogen would be reduced. But again, you'd get an electrochemical cell based on these values. So basically the table is arranged in order of increasing strength of the oxidizing agent. So fluorine gets reduced, very strong oxidizing agent. Lithium pretty well always gets oxidized, so it's a very weak or very strong reducing agent, weak oxidizing agent. Okay, so that's how that table works. So we can use that table to establish overall equations and cell potential. So let's get started on that. So we're going to look at this galvanic cell made up of chlorine and sodium. So the first thing we want to do is be able to go have a look at the table and find our two cells. So back to the table, and what we're looking for here is sodium, which is down near the bottom. So here's sodium, and chlorine. And so here's chlorine up here near the top. Okay, so here's our 2 reduction half reactions. They're both written as reductions. And remember that memory aid, REDCat, reduction occurs at the cathode. So chlorine, being the stronger oxidizing agent, will be reduced, greater positive value, and that means sodium will be oxidized. Okay, so you just want to keep that in mind. So now we can start constructing or putting together how they're going to determine the equation for this galvanic cell containing chlorine and sodium. So first thing you want to do is write down the two reduction half reactions. So there they are, written both as reductions. Chlorine plus electrons yielding 2Cl minus, sodium plus an electron yielding sodium solid. Okay, next, rearrange the half reaction at the anode. Now remember, we mentioned that this is a stronger oxidizing agent, the chlorine, so it gets reduced. And so if it gets reduced, that means it's going to act as a cathode. So that means sodium's our anode. And at the anode, we have oxidation. And if we want to represent the equation properly, we have to rewrite it, because we initially get it as a reduction, so we rearrange it to write it as an oxidation. So now what we have is an anode as an oxidation half reaction and a cathode as a reduction half reaction. Okay, we have to make the electron transfer equal. So if you notice here, actually I'm just going to get rid of it. We don't need this one anymore, so we can kind of ignore it. So we have 2 electrons being gained by the chlorine gas. We have only a single electron being lost by the sodium. And so we have to make that electron transfer equal. And to do that, we multiply our oxidation half reaction by 2. So now we have 2 sodium ions yielding 2 atoms plus 2 electrons. So now the electron transfer is equal 2 and 2. So equal electron transfer. So that's something we want. And then finally, we simply add the 2 half reactions together. We add them. Don't forget, it's all addition, so it's easy math. So now we have a balanced overall reaction for this galvanic cell, for a chlorine-sodium galvanic cell. 2 sodium ions plus chlorine yields 2Cl minus plus sodium. Okay? And so that's really about all there is to it in terms of determining the overall equation. All right. What about determining the cell potential? Well, let's look at this same cell. So just quickly go back to the table. So the cell potential is this voltage that we're going to generate, this spontaneous generation of current. So back to our 2 equations. There's our 1.36 volts for the reduction half reaction of chlorine. And down here we have minus 2.71 volts for sodium. So we have our 2 cell potentials that we also get from our standard reduction table. So now, how do we change things? Well, there's our 2 reduction half reactions, and now I've included our standard potentials for those reductions. Those are both reduction potentials. All right, so remember we rearranged our sodium half reaction to make it an oxidation, and when we do that, we reverse the voltage. So it is negative 2.71 as a reduction. I've reversed it now. It's positive 2.71 as an oxidation. Okay, we multiplied our half reaction by 2 to make the electron transfer equal, but here's a really important bit. We did not change the cell, E cell, for this half reaction. It stays at 0 or at positive 2.71. So you multiply the elements and the electrons by a coefficient, but you do not change the cell potential, because the cell potential is not based on stoichiometry, it's based on standard conditions, which would be concentration or pressure, depending on what it is. So again, it's really important you remember you don't change the E naught for the cell when you multiply something. And then finally, like we did with the half reactions, we simply add the cell potentials together. So it becomes plus 1.36 plus 2.71. So now we have an overall cell potential of plus 4.07 volts. So if you set up a galvanic cell comprised of sodium and chlorine in this fashion, you would generate 4.07 volts of current. Okay, so that's it, generating an overall equation and generating a cell potential. Well, let's look at one more example. So determine the overall reaction and cell potential for a galvanic cell made up of Fe2, Fe3, and aluminum. So first thing we have to do is go to the table and find our half reactions. So Fe2 plus Fe3 plus, well, here it is right here. Okay, as a reduction, Fe3 plus an electron yields Fe2 plus. So that's a gain of electrons, reduction. And the other one is aluminum. So aluminum is way down here. Aluminum 3 plus 3 electrons yields aluminum solid. So there's a reduction. And so there are our two half reactions. Now remember, REDCat, reduction occurs at the cathode. So which is the stronger oxidizing agent? That's the iron ion. And so it will be reduced. Reduction occurs at the cathode. So this is going to be our cathode. This is going to be our anode. And remember, we have to reverse the half reaction at the anode. Okay? So here are our two half reactions. Fe3 plus yielding Fe2 plus. There's the half cell potential. Aluminum yielding aluminum solid. There's the half reaction cell potential. And so as I just mentioned, this is our anode. So we reverse it. And so it becomes aluminum solid yields aluminum 3 plus 3 electrons. And so we reverse our cell potential. So that becomes positive 1.66 volts. Okay, and so we're done with that half reaction, so you might as well get rid of it. Now, the other thing is the electron transfer is not equal. Remember, 1 electron and 3 electrons, we have to make those equal, so we're going to multiply our cathode half reaction by 3. And so there we go, multiplied by 3. Now we simply add everything together, and that includes the cell potentials. So in terms of overall equation, we have 3 Fe3 plus aluminum solid yields 3 Fe2 plus aluminum 3 plus. And we have no free electrons. They have vanished, so to speak, in the course of the oxidation and the reduction. Now we simply add our E naught together to get our E naught cell. So the overall cell potential, so 0.77 plus 1.66, and that equals 2.43 volts. Positive 2.43 volts. And so there you go. Positive cell potential. For a spontaneous generation of current, it's always positive E naught cell, and so that is the case for all galvanic cells. Galvanic cells, spontaneous generation of current, positive E naught cell. Okay, so just quickly in conclusion, things to remember when you're determining the overall reaction to cell potential given the species involved in our galvanic cell. Firstly, REDCat, reduction occurs at the cathode. You have to decide which half reaction is your reduction half reaction. You have to decide which half reaction is your oxidation half reaction. So remember this handy memory aid, and the more positive cell potential will be the anode. Second thing, reverse the half reaction at the anode. That is, make it an oxidation half reaction. Remember, they're all given as reductions. Oxidation occurs at the anode, so make it an oxidation half reaction. Thirdly, reverse the E naught cell at the anode, so for that newly created oxidation half reaction. So you reverse the value. If it's a negative value, it becomes positive. Fourth, make the electron transfer between the two half reactions equal by multiplying by appropriate coefficients. You've already done that. That should be familiar to you. Finally, add together the oxidation and reduction half reactions to get the overall reaction. Actually, that's not finally. Finally, add the two E naughts together, the E naught for the oxidation and the E naught for the reduction, to get the E naught for the cell. So if you follow those 6 steps, it's really quite straightforward coming up with the overall reaction and the cell potential for any galvanic cell. So that concludes this video.